talk here. We've got Alex Miller again. Some of you might remember him from about 40 minutes ago when he did his first talk this morning. But this one again is about high temperature oscillating heat pipes, and
we're gonna move quick here. So this is a pretty long deck, and so half a dozen of these slides probably should have been in an appendix for a 15 to 20 minute talk. So the approach here will be that quite a lot of the setup background slides, kind of here for completeness in the proceedings, but I'm going to click through them with low, narrative support, and then we'll get to the good stuff in the latter half of the deck. But this work is looking at very high temperature OHP development, primarily for leading edge applications, but will inherently have other applications outside of that space. So this is work that's been ongoing for about 3 years with NASA on another phase 1 and phase 2 SBIR program. PI Dan Pounds, who I think is trying to call in, and myself. So presentation outline, look at that original solicitation that we were responsive to, goals, targets, and our proposed solution. Overview of the phase 1 work, and then overview of the phase 2 work that we are now essentially at the end of the phase 2 period of performance. All right, so the goal of the program was to develop a wing leading edge skin structure with novel integrated thermal management using our flagship technology, the OHP. The SBIR timeline, we're here actually on a no-cost extension to complete some kind of high-value testing that we really wanted to complete on the program, but this program's essentially wrapped up. The original solicitation from NASA that we submitted the proposal to was looking for these 4 items in particular that really resonated with what we were thinking at the time on the program. And so these are looking at manufacturing approaches that can fabricate complex devices such as heat pipe cooled leading edges, lightweight materials that can repeatedly reach high surface temperature, capabilities to fabricate complex geometry, incorporating integral heat pipes and multifunctional structures, where you incorporate thermal management and structural load capabilities into a integrated component. So a lot of buzzwords here for us in general in terms of multifunctional structures and sort of integral thermal management. So our proposed solution was to develop the first high temp OHPs, looking at 600 up to potentially above 1,000 degrees C, which at the beginning of the phase 1 3 years ago had essentially never been demonstrated. Show high heat flux capacity, hundreds of watts per square centimeter input in the evaporator. Show low thermal resistance, similar to liquid metal conventional wick-based heat pipes, and then this multifunctional structure. So at the beginning of the phase 1, we performed a case study to highlight, the utility in actually using an OHP structure, and in doing so compared it to solid metal. So the focus here being comparison to other metallic hot structures, not necessarily towards ceramic matrix composite development. But looking at this case study, we sort of did a little bit of self-teaching about aerothermal heating for hypersonic leading edges. And the output of this is looking at what sort of fluxes are generated at the stagnation line for modest radii, not super sharp, but quarter-inch type radius leading edges at Mach 6 to 8. You generate these sorts of flux levels at that stagnation line. So there's a couple important relationships to understand the general thermal map. That's at the stagnation point. Heat flux varies inversely with the root of the radius. So as you go to very sharp leading edges, the flux rises rapidly. As you go up in Mach number, the flux rises with the cube of the Mach number. Hence the general thermal problem as we push the envelope on these hypersonic vehicles. And lastly, how that flux varies radially as you move off the stagnation line point. It actually drops really closely to cosine as you move back around this leading edge. So back in the phase 1, we did a series of finite element simulations, And one of the takeaways was we think compared to a solid Inconel leading edge structure, which isn't really really competitive solution for hypersonic leading edges. But if you were looking at that sort of metallic hot structure and you simply converted that structure to including the embedded microchannels and working fluid and had a functional OHP, then you could drop that peak temperature at the leading edge by 250 K at around Mach 6. So we looked at various sensitivities to different channel densities and transport lengths shown by these other series. But the key takeaway is that OHP enables essentially more aggressive heat input conditions related to higher Mach number flight conditions for some given materials working temperature ceiling. So if you're working with a Inconel type superalloy, you might have a mature understanding of the maximum service ceiling in terms of the yield strength of that material or other properties, and by producing the same structure but instead of being a solid conductor, making the OHP, we can vastly improve the thermal characteristics, the ability to transport heat, but retain most of that structural integrity. So the phase one hardware did not go for gold with the really complex leading edge wedge geometry required, but we went with simple 6-inch scale breadboards because the first push here was to actually demonstrate viable working fluids and functional OHPs in simple geometries, and then a pivot from there to complex geometries. So we started with traditionally manufactured CNC and vacuum brazed breadboard OHPs at 6-inch scale. You can see one here, and the heat map. The way they were actually tested, we took this notional future form of the a leading edge geometry with a high flux input on the wedge. You transport the heat back and radiate off the adjacent surfaces, sort of with some sort of like near adiabatic internal surfaces in the wedge. And if you flatten that out, you basically get what we tested in phase one and actually in most of the phase two as well, in terms of centerline heat input and then radiation and free convection in our test bed off the adjacent surfaces. So here we see a picture of that phase one test bed, the CAD and the physical one. We worked with two different heat input geometries, a 1/4-inch long contact patch and a 1/2-inch long contact patch formed by the physical interface with these molybdenum blocks that we used with commercial off-the-shelf sort of Incaloy sheet. Cartridge heaters were fed inside. We applied electrical power that was driven into the OHP evaporator at this clamped interface. TC map shown on the right. We have TCs essentially in the heater block and on the physical rejection surface, but also on the backside where we sort of have that adiabatic boundary, but ability to place TCs there as well. So the phase one testing, on the bottom, we can see a test of this solid Inconel control. This is done before we had insulation on the heater block, but photo in the center bottom with the simulation on the left, time series on the right, essentially showcasing the poor thermal conductivity of just an Inconel plate. And then at the top, we have essentially a mass equivalent OHP, also made out of a Inconel envelope, but with working fluid inside. And we can see, the contribution of that working fluid, ability to axially transport the heat and isothermalize the rejection surface. So nice hot part. You can see it reflected in the simulation and just visibly to the eye in the photograph of the test itself. So here we simulated, expected about a 9x improvement in conductance, and we actually saw very close to that. This is a prediction of simulations run before testing, and the experimental work actually showed a very similar improvement, about an order of magnitude better performance thermally than the solid Inconel plate. So coming from effective thermal conductivity of the base envelope, on the order of 20 watts per K, up to like a aluminum or better type number, but of course with much higher service temperature than you would see from aluminum or copper. All right, so we have a little catch-all summary slide here from phase 1. Built and tested the first high temperature, high performance OHPs, validated the startup limit. We were able to, this is the onset of nucleate boiling, and in some of the time series plots, you can maybe see it here. You see the DT across the device, the spatial gradient drops sharply when we hit a new power step, and the fluid temperature rises. You see that spatial gradient improve sharply, and we attribute that to the onset of nucleate boiling, which is well predicted by this red curve in the limits chart. And demonstrated actually 2 working fluids during that phase 1, and these, to the surprise of most people, were not liquid metals. These are different elemental fluids that have high vapor pressure. Demonstrated a manufacturing process, so a little bit of MRL development in the phase 1 to prepare for the desire to produce wedge geometries in phase 2. All the phase 1 testing was testbed limited, did not reach any OHP transport limits, but we were able to demonstrate these key characteristics shown in bullets, get up to just over 1,000 degrees. At the input surface of the Inconel envelope, input flux is a little over 100 watts per square centimeter. At the evaporator, 70% effective density of the outer envelope of the same geometry Inconel due to the void space and the lower density fluid charged inside, and approximately 8x conductance of the envelope itself. So moving to phase 2, a variety of technical objectives and task descriptions, actually an updated program targets that were largely copy-pasted from a DARPA program and called MOC. It's an acronym, but looking for a wedge that can take high input flux and survive up to high temperature. So on the phase 2, we did a variety of testing with, these are organized by the way we heated the part, and the heating configuration in the test bed. And here we have a single heater applying heat to the top center line of the part, and radiation and free convection from the adjacent surfaces. We pivoted to using a different working fluid, which is liquid metal. We have improved chemical compatibility with the envelope materials of interest, superalloys, wider operating range than the fluid shown in phase 1, higher critical point and lower freezing point, both valuable. And again, with this new working fluid, we've been able to experimentally demonstrate a predictable startup in relation to the OHP limits of operation. Originally, pioneered by Bruce Drolan, and he actually made an update to the startup limit to better match the startup experimental performance we're seeing with the liquid metal working fluid. Dashed in the boxes in the lower left, we took one of the phase 1 OHPs out of storage after 18 months, lit it back up, and it works nicely after 18 months of storage, actually with the working fluid frozen. And shown on the right, just an IR comparison, again showcasing qualitatively, to some degree, visually, the sort of isothermality that we can see with the OHP microchannels embedded in the envelope. There's a time series on the right. Could spend more time than we have talking about this chart, but the gist is we have instrumentation in the heater, and then opposite the heater, we're calling opposite evaporator, and then some of the condenser surfaces. As we rise in the electrical power steps, and as the temperature of the structure comes up, you can see a feature here, as we're, the system's getting hotter, you see a dip in the opposite evap temperature and improvement in the overall structure's uniformity as measured from that evaporator out to these tips of the part, about 3 inches away from the heat input source. So that closes up these series, tighten up, showing improved performance actually as you go up in temperature and power. So we're transporting more heat with lower gradient. So the quotient there is showing, steadily improving thermal conductance. Well, we wanted to go even hotter. Here we're getting up to 675 with the condenser. We wanted to go hotter. So to do so, we needed a second heater block bolted up opposing the original one in this sort of clamshell sandwich construction. So we were burning up lots of those Incolloy cartridge heaters. And now with 2 cartridge heaters, we're able to run higher powers. So at 1.2 kilowatts electrical in this configuration, we're able to drive the condenser surfaces up to 850C. And we internally like this picture on the right a lot, generated a lot of excitement internally at Thermovant to see ability to make these really hot OHPs that are showing good performance. One asterisk on this testing is, we don't actually truly know the physical evaporator temperature, as the thermocouple probes are embedded essentially on the hot side of the thermal interface next to the adjacent the cartridge heater. So we know the heater temperature and we know the OHP condenser temperature, but the delta there includes a series thermal resistance from that thermal interface. Okay, so what's next? So we had shown the center heating, but the transport distance is only on the order of 2 inches. So the full width of the part here is 5 1/4. So we shifted the heater to the edge of the part to try to drive that heat instead of 2.5, more like 5 inches across the part, explore larger, longer transport distance. And it worked well. And on this test, we got, air quotes, lucky. The cartridge heaters survived with the actual, heater blocks running, at the order of 1100 degrees C for this testing, and we're able to get the OHP condenser up to 950C. So this was a really nice test. We're actually, starting to approach the envelope surface temperature of that Inconel 625 envelope. The vapor pressure of the fluid inside is actually quite low, as is the nature of the liquid metals in this temperature range. So not at risk from a factor of safety to pressure containment, but just out there where the yield strength of 625 has really fallen off the cliff. So that's where we pull the plug on pushing the temperature. All right, so yes.
We got about 3 minutes left.
Excellent. Okay, so our last breadboard geometry, these planar geometries we tested, was significantly larger, 13.5 inches long, operated in a similar manner. And you can see on the right where we put on some KO insulation to provide an adiabatic actual transport distance, where we have a remote condenser. So center heated, it's got a transport on the order of 6 inches to a net rejection surface. This worked really nicely, just like the 6-inch scale parts as shown by the IR and the visible here. Again, heat input, about 6-inch transport, able to drive heat out to an 800C condenser. We have clear, repeatable, and predictable startup at about 550 degrees adiabatic temperature, and actually quite low power. Onset of nucleate boiling here, we can see the spatial gradient in the part fall off a cliff from 500C down to 100 or so, and then again steadily improving performance with temperature and power. And that's plotted here in the lower flux along with the lower plot, along with the axial flux on the secondary vertical axis. We're actually pushing here, coming up on 2 megawatts per meter square of the transport cross section, which is a number that's been of interest to some of our folks interested outside of NASA. Okay, so I only have a minute here. So the grand finale was to go from the breadboard geometries that have been demonstrated to the application geometry, a leading edge wedge geometry with this 1/4 inch radius. So these were additively manufactured and tested successfully. The operation was similar to the same liquid metal working fluid in the planar breadboard geometries of the same scale. So here we're again using cartridge heaters to drive heat into this sort of tangent point right in the working fluid sweeps through the envelope here, drive the heat right into that tip of the working fluid space. So we're able to a variety of pictures here. The lower one, this is a borescope inside of our argon purged box. Here's a top view through the viewport, able to drive this this part, additively manufactured powder-based method in Inconel up to 675 at the condenser surface. And we ran the exact same part vented of a working fluid, that time series data shown in the top here, where you can see approximately an order of magnitude increase in the conductance of the OHP as opposed to the mass equivalent, Inconel structure. It's just vented as our favorite control. Some more plots here comparing the thermal resistance to the rejection power. I don't have enough time to talk through these in detail, but one takeaway is that our predicted startup temperature is shown here in the dashed series, and where it intersects with this condenser temp, is our essentially predicted startup temperature, and this prediction made before the test itself for this wedge. With your eye, you drop down to the thermal resistance. You can see this is a pretty reasonable startup prediction in terms of the evolution of the improvement in the part with power matching the predicted startup temperature in QT space. Again, on the right, we have a comparison of the control, the mass equivalent control thermal resistance to the OHP, and about an order of magnitude spread here. So we took these experimental results, took it back into the simulation environment, and essentially just turned the knobs we have in the finite element environment to match experiment, and then we can hence extract that thermal characterization of both the channel volume and the convective film coefficients applied to the walls, and we can utilize that for predicting performance of essentially other designs and varying boundary conditions. So in summary, high temperature, we call that, perhaps 400 to 1100 degrees C. Oscillating heat pipes and superalloy envelopes have risen to TRL, MRL4 through this effort. We've made complex, additively manufactured and up to third meter scale geometries successfully, so high yield in the manufacturing and successful OHP function. So the phase 2 demonstrations with the new liquid metal working fluid are very promising. So we have good thermal performance, a manageable freeze point, and what's sort of really important to us, because it was not the case in phase 1, is that we have sort of a heritage of these liquid metal working fluids with superalloy envelopes. So the compatibility and corrosion risk is low, and we're pleased with that. No hot limit. So transport capacity limitation of the structure, due to very high input flux or some other condition has been observed in any testing to date. Somewhat unfortunately, we would love to be able to validate the predictions of how much heat these structures can transport, but we just weren't able to get there with the existing test bed. Power limitations, able to push up to about 2 kilowatts electrical, and also not able to show sort of a what is the temperature limit of these liquid metal working fluids, because we aren't able to push above, probably 1100 C on the Inconel envelope. So perhaps 1000 C fluid temperature. We would have to go up to, maybe like a niobium alloy type envelope in the future to really see where we run into, transport capacity limitations just due to temperature. One last takeaway is that our ability to modeling of these extreme temperature OHPs is improving pretty rapidly in the last several months due to testing, as we can now generate this empirical data sets to verify, validate, and anchor the models. And then thanks to the team. So Dan and I largely leading this effort together for a couple years. A lot of engineering support from Patrick Margavio, and then some consultants, and then another big thanks to Val at Langley and Tim Gabb at Glenn for tying in with us and providing guidance over the. Thanks.
Yeah, thanks, Alex. That's very, very interesting, very cool. Yeah, I'm going to keep my eye on this work as you guys continue here. The 1100 C heat pipes, that's pretty cool.
I guess if you're not shutting me off yet, I'll say a couple more words. That there's been a lot of really good materials development recently in the ceramic matrix composites, carbons, carbon-6, and things that seem to be essentially meeting some needs of hypersonic vehicles. And There's only moderate, interest right now in trying to push for, OHPs, at this kind of 600 to 1,000 range for leading edge applications. But we're also very interested in leveraging them in different form factors for other things, other areas in, propulsion systems, solid oxide fuel cells, in general, any place where you might have need for, some structural component that's traditionally been metal for, surface temperature, but, ability to greatly improve their thermal properties.